All right, so let's start by reviewing what we did in the last class with this NDSolve and using NDSolve in a piecewise way. We have this differential equation. Let's write this on the board. Dx to t equals negative x. We added an initial condition, x of 0 equals 1. This initial value problem has a unique solution. We saw that it was x equals e to the negative t. That function solves that initial value problem. It solves the differential equation. Its derivative is the opposite of itself because of the chain rule. And it satisfies this initial condition. Because it's such a simple differential equation, we don't have to use NDSolve to solve it, but we can. So here again is the syntax of NDSolve. You've got the differential equation right here. You've got the initial condition right here. I'm storing the information that ND solves in a variable called solution 1. It's this interpolating function stuff. Somehow is stored in solution 1. I can access that information through the use of this command called evaluate and the slash dot in the way that you see here to create, ultimately, a graph of the numerical approximation to the solution. In the last class period, we also talked about changing the location of the solution at some other moment in time, so that in a sense we got two pieces to the solution. One piece came from this particular initial condition. Another piece came from this condition. Ultimately, when you put this together in a piecewise way, you create a discontinuous function, each piece of which solves the differential equation. And it satisfies the two conditions, x of 0 equals 1 and x of 2 equals 1. Let's go ahead and enter this and plot it down here. Already plotted, but the blue graph you see is the solution of this initial value problem, the continuous solution. The red graph matches that solution because it starts with the same initial condition that x of 0 equals 1, but then I decided at time 2 that I wanted the condition to be back up to 1. So we got these two pieces to the graph that is analogous to changing the velocity vector for your project to help the rocket get close to the moon and hopefully into orbit with it. What do I want to do, though, in this class period? I'd like to allow myself to have a different moment in time when I have the discontinuity. So I'm going to change this 2 to a letter, like t. And I'd also like to change the output to not being something specific like 1, but to be some other parameter value. I'll call it new init, to kind of stand for a new initial condition, though it is going to occur not at time 0, but at time t. If I do that, however, then solution 2 really depends on capital T and new init. So I need to think of that as a function of capital T and new init. Enter it like that. Oops, I better clear. Let's see. I think I need to clear something, perhaps the X ahead of time. Do that? No. All right, we're having problems here. Let's go ahead and quit the kernel. Re-enter solution 1 and solution 2. Hopefully we won't run into a trouble now. There we go. Okay? So I got solution 1. I got the value, the output of NDSolve stored in solution 1 up here. I've got the output of NDSolve down here stored in solution 2, and it is a function of capital T and new init. I found out in the last class period that doing it in this piecewise way wasn't working. So to get a manipulate animation for this situation that will allow me to see essentially this kind of graph for different moments in time where the discontinuity occurs and different outputs for the new initial condition, I needed to do it in kind of a non-ideal way that I discovered in between classes. So this, first of all, is going to be a manipulate that's going to make an animation. What am I going to animate? Well, first of all, I'm going to animate the right endpoint of the plotting interval that I've typically called B. I'll start at just barely bigger than 0, 0.0001, and go up to 3, because that was how far I let the NDSolve go up to. It's 3 in both cases. I also want to let the moment in time, the capital T, where the discontinuity occurs, to vary. I'll start its value at 2, and I'll let it go down to, say, 0.1 and up to 2.9. Okay, that's the syntax that will allow capital T to change in that way. And I'll allow the new init to change. I'll start at 1 and allow it to go down to 0.1. Okay, so this will create 3 sliders that will allow me to change all those things. All right, here comes the tricky part. This was a solution I found in between classes again. It's not ideal perhaps, but we're going to go ahead and use it. I'm going to use a command called the if command. And the syntax of the if command is this. It's got 3 inputs. The first input of which is a condition. If that condition holds, if it is true, then you get 1 output. Else, if it's false, you get another output. This perhaps is not the most ideal way to do what I'm about to show you to do, but it is one way that worked. Hopefully I'll be able to get it working for you here today. I'll go ahead and put the commas in there, like you see. What condition am I after? Well, what I'm really after here is I'm after a graph that when B changes is going to be animated like this. You'll see the first part of the solution, and all of a sudden when you get to time capital T, it'll jump up here and you'll see the second part of the solution at the new init value. That's what I'm after. So keeping that in mind, the real key here is what happens when you reach B equals capital T. How do you get it to make that change? Okay, so my condition is whether B is less than or equal to capital T. If B, the right endpoint of the interval that I'm plotting this over, is less than or equal to capital T, then I'm just going to plot this first piece. And I don't need a show for that. On the other hand, else, if B is bigger than capital T, I'm going to want to see this whole graph and the part of this graph up to time B. And I found that I needed to use a show to help me do that. So let's see if this works here. So again, if B is less than or equal to capital T, I'm going to make a plot of the solution up to time B that comes from solution 1, not solution 2. So I can use the evaluate x of t slash dot solution 1 based on the initial condition x of 0 equals 1. From time t goes from 0 to b. Probably going to want to have the whole plot range in there all the time. 0 to 3 in the t direction and say 0 to 1 in the, actually let's go 0 to 3 in the vertical direction as well. What about if b is bigger than t? The condition you see here is b is less than or equal to t. When that happens, you make this plot. Else, otherwise, when b is greater than t, you're going to get output that comes from what comes out of the comma here. I'm going to want to combine graphics there, so I'm going to use a show. I'm going to plot the entire graph from solution 1 as t goes from 0 to t instead of b. So let's copy and paste that. Change the b to a t, a capital T. I want to combine that with another graph, the other piece that comes from solution 2. From capital T up to little b. So essentially, I think I can copy and paste it again, change the solution 1 to a solution 2, and also remember solution 2 depends on capital T and new init. So I'll put a capital T and a new init in there. And some stuff is red, so that I must have syntax errors here somewhere. Let's see. That ends the solution 2, this ends the evaluate, this ends the show. I don't see any more red. I'm going to go ahead and risk it here and see if it works. Cross your fingers. No errors so far. Let B go until you reach capital T. Whoops, and now we have errors. All right, what happened? This worked on my computer. Can I do something different now? I think this might be a problem. In the second one, I need to change this here to be capital T. I hope that does it. Not, let's see what happens. Well,
You need to wrap in the second plot. You need to wrap both the evaluates within curly braces because you're plotting two of them.
yes. Let's see. Where are you talking about?
Right there where your cursor is. Because you have two separate evaluates.
Yeah. Let's see. This is grabbing up to time capital T.
You need another plot.
That's it. Plot. I forgot my plot. I hope that's it. As okay, I gotta put the T goes from capital T to E inside there. Let's see if this works. Well, sort of. I need to make sure the plot range is included as well. Okay, you can see it's easy to forget lots of things. This is going with the if. The previous one goes with the show. Put the plot range in there. There we go. Well, it did change where the origin was slightly. I don't like that, so I can fix that. Axis origin. 0, 0. That's still cheating. Maybe I need it in both spots. All right. Well, I think that basically does it here. It's still sort of shifting in this range. Okay, but this it's basically working. Okay. I can now change capital T back and forth. I can also change the new initial condition. Okay, so doing something like this is one way to attempt to try to allow yourself to vary the moment in time that you change the spaceship's velocity and also change that new velocity. It's going to probably be shorter, maybe in the same direction as the velocity in the moment in time when you make the change. Maybe you want to modify the direction a little bit. Try it initially keeping the direction the same and just make it shorter. And hopefully, through enough experimentation, you can get it to go into orbit in an analogous way. Part of my motivation for the project is just getting you to experiment like this. Okay, and it is frustrating. I know sometimes I get frustrated too because we run into these errors. But you have to keep working at it. If you keep working at it, look at examples and get help from me. Hopefully we can get these things working. And you can come for me with help, for help on the mathematics. All right, let's go on to the other two main tasks for today. The second task is we want to explore what I call wild functions of more than one variable. Actually, I was introduced to this by Dr. Wetzel. He called these wild functions, so I call them wild functions. You've got a graded problem due on Monday that's going to be related to what I'm about to show you. First of all, by the way, you should have seen some wild functions in the past. What do I mean by a wild function? I mean functions that you're not used to, that do some crazy kinds of things. Here's the one I'm thinking of that you perhaps should have seen in the past. Does anybody happen to know what this one does? You think the graph of this looks pretty ordinary? No, it doesn't. That's my problem there. There we go. Isn't that cool? What's going on there? It's kind of weird. Is that an error? It's not perfect, but it's not an error. It's hard to draw this graph perfectly. Let's go in by a factor of 10 to being between negative 0.3 and positive 0.3. It gets crazier and crazier. What in the world is going on there? Again, it's not a perfect graph, but at the same time, it's not really an error. What's going on here is this graph is oscillating infinitely off on any little interval around 0, no matter how small. there's infinitely many oscillations. That's a wild function, okay? What's going on is, as x goes to 0, for example, from the right, 1 over x is going to plus infinity through all positive values. So the sine function, the sine of that input is going through, it's got to go through infinitely many oscillations as 1 over x goes to infinity. Equivalently, as x goes to 0 from the right. So if you think about it in that way, it's got to do that kind of thing. But it's an example of a wild function. Here are a couple examples of wild functions in multivariable calculus. You might want to write these down. F of xy equals x squared divided by x squared plus y squared. What's wild about that? Well, the first thing you should notice is that you would be dividing by 0 if you plugged in the origin, x equals 0, y equals 0. You might expect that there would be some sort of higher dimensional vertical asymptote then at the origin, but there's not. Instead, there's some sort of weird folding V shape, seemingly. Actually, if we made the numerator just say 1, then we would get a vertical asymptote, a higher dimensional vertical asymptote. Is that really? If you change the plot range to being, say, 0 to 3, 100, you see it really is some sort of higher dimensional vertical asymptote. All right, let's go back to the original example. Get rid of the plot range. What's going on here? Well, first of all, the opening V shape that you see in there is actually numerical error. The graph doesn't really look like that. If you force Mathematica to plot more points, say 100, both the x and y directions, it does get rid of the v to a certain degree. So it really is not doing that. It is undefined at 0 at the origin. X equals 0, y equals 0. And there is some sort of folding going on with this graph. And that folding that you see here causes the limit as you approach the origin to not exist. Could you prove that? A contour plot helps us see how we might prove that a little bit more rigorously. Remember, with these contour plots, you're looking at, it's called the contour map in the book, the level curves, the curves on which the function is constant. Along each of these straight lines, in this case, that go through the origin, the function is constant. And the values that you see here are all different, which does match the shading. The lighter shading corresponds to higher values, in this case, 0.9, 0.8, 0.7. Darker shading corresponds to lower values like 0.1 and 0.2. And all these different contours, level curves, are converging together on the origin. That's got to mean the limit as you approach the origin doesn't exist. Is there a more rigorous way to prove that, though? Essentially, you can consider this function along lines of slope m. So f of xy, you write the equation up here, is x squared over x squared plus y squared. Along a line through the origin of slope m, what happens to the function? What you can do is you can replace the y with mx. To really get a function of just x, think of the m as constant. What is that function? Replace y with mx. What do you get? Well, as long as x is non-zero, you're going to get 1 over 1 plus m squared, which, if m is fixed, is a constant. But different constants for different values of m. So what this is showing you is along different lines to the origin, it's confirming the value, the output of the function is constant, but different slopes produce different constants. Okay, and that's a little bit more rigorous way to say that the limit, not perfectly rigorous, but it's a little bit more rigorous way to say that the limit of this function as the point goes to the origin does not exist. Because if it did exist, then the limit would have to be the same no matter how you approach the origin. Okay? Your problem, that's somewhat similar to this, is a bit trickier, a bit stranger. This particular function is similar to the one that comes up in your problem. Not exactly the same, but similar. It's f of xy equals x times y squared over x squared plus y to the fourth. What happens with this function? You make the 3D plot. You see a similar kind of folding, but at the same time it's also different. It's a little crazier looking. You also see sort of an opening there, like a V shape. That again is some numerical error. You got to plot a lot more points to sort of get rid of that. Let me try 500. Watch that. Both the V that's in the upward direction and in the downward direction should close up. That's the numerical error that we're seeing there. Function is incorrect. Okay, let's see. I believe those should close up. It takes a while when you want to plot that many points. There it is. It did close up. See that? Okay. So there is some sort of strange folding going on near the origin. And it's interesting that you can kind of see some parabola kinds of shapes when you look at this. What ends up happening if you look at the contour map through contour plot is that once again different level curves converge on the origin through different values because you have the different shading, but these are sideways parabolas instead of straight lines. Pretty interesting. If you think about what happens to this function along straight lines that go through the origin, again, replace y with mx, you don't get a constant. What do you get? With the calculation, replace y, up in that formula over there, with m times x. Some cancellation can happen. Let's see. Oops, I made a mistake today. Yeah, sorry. My eraser. Let's go. Replace y with mx. Yeah, this is the fourth power here. Okay, so you're going to get 1 plus m to the fourth times x squared. The x squareds will cancel as long as x is non-zero. So as long as x is non-zero, you get this expression, which is not constant. It does depend on x. This was supposed to be an x cubed here, wasn't it? There is one x still up in the numerator. It's not a constant function of x, which is confirming that the function is not constant along straight lines. Moreover, as x goes to 0, this does have a limit. The limit of this is 0. If you approach the origin along any straight line here with slope m, the limit is 0. So does that mean the overall limit is 0? No, it doesn't. Because now if you approach along one of those parabolas, those are sideways parabolas. They have an equation x equals some constant a times y squared, because they're sideways. X would be a function of y. Replace x with ay squared and see what you get. Again, look at the formula up there. Replace x with ay squared. That formula way over there. Every x gets replaced with ay squared. Catch me if I make any mistakes. We've got a y to the fourth on top. We've got y to the fourth in both terms on the bottom, so it can be factored out. And again, as long as y is non-zero, those can cancel. So when y is non-zero, you get that which is a constant. A is constant. Along any one of those sideways parabolas, A will be constant, and the output of this function is constant. But different A's, different parabolas are going to produce different constants. And so that means the overall limit as you approach the origin does not exist. You can't just look at straight lines. You have to allow yourself to look at curves too. These are wild functions. This is going to be atypical of what we encounter. Typically, most of the functions we encounter will be tame instead of wild, and the limits will exist. But you should be aware of these examples. All right, the last thing to do today is to go back to the density example and talk about how to interpret the partial derivatives. So again, I'm trying to put most of the content from chapters 14 and 15 into the context of, well, you could think of it as a physics example. That's probably the easiest thing to imagine. Imagine a thin plate of metal, and here initially we were thinking about it on the interval between -5 and 5 in the x direction and -5 and 5 in the y direction. Go ahead and enter the function here. Here's the 3D plot. You make the plot range go from, in the z direction, go from 0 to 400, say. And we see that it does stay above 0, so we never have a negative density. You can think about units for this. If it's talking about a thin sheet of metal, we imagine the thickness is essentially 0. You can think of this as a density in units of mass per unit of area, for example, grams per square centimeter. When this function is higher, that's when the metal is more dense. You shouldn't think of this graph as being the actual metal, by the way. Okay? This is not the metal. It's not shaped like that. This graph is showing you the density as a function of the location of the metal. So where this is higher, that means the metal is more dense. In that area where it's lower, it's less dense. We don't worry about practicalities like how would you make such a sheet of metal. Don't worry about it. Maybe it's not even possible, but we pretend that it's possible. Contour plot can do this as well. It is perhaps more permissible to imagine that this square is the actual sheet of metal, and that these contours are telling you the density at various points. And again, if you put the cursor on any one of these, like right there, that's telling you at that point the density is 289.8 grams per square centimeter, which again would mean if you cut out a little piece of metal near there, you can approximate its mass by multiplying that density times the area of the little piece. It will be an approximation because this is a function that varies. It's not constant, but over a small piece, it doesn't change very much by the continuity. All right, the main thing to do today here with this is to try to understand what the meaning of the partial derivatives are. So let's write those down again. Let's see the formula. So in your completion homework for today, you had problems where you're calculating partial derivatives. I hope you felt like you started to get good at it. All right, we took the partial derivatives the other day on Monday. Again, here's the notation. It's okay if you look at this and you say dz dx, that's okay. You can think of this as sort of a fancy d if you like. Some people say it that way. Other people say partial. They'll say partial z, partial x, to emphasize it's a different symbol and that it's a partial derivative. Anytime you've got a function that's got more than one independent variable, its derivatives with respect to each variable are called partial derivatives. Which kind of implies there might be some sort of total derivative as well, and in fact there actually is, but we're not going to talk about that right now. Another notation that you saw in the book that I didn't show you the other day is to use a subscript. F sub x means the partial derivative with respect to x. That's another notation that you can use. We will be okay with being sloppy, okay? This is a function of x and y, so in reality I really should write that. But this is a situation where I will be okay with you being sloppy to save some time. You don't have to write the dependence on x and y. Treat the y like a constant. You're going to get 3x squared plus y squared minus 10. Similar kind of thing for the partial derivative with respect to y, which can also be written f sub y. Once again, you can be sloppy and don't worry about putting the x comma y there. Though when you do plug in a point, a specific point, then you should put the x comma y in there and their specific values. Also, when you use mathematically with this, you do need to plug in, you do need to treat these as functions. Do that as well. Treat the x like a constant, so the derivative of x cubed will be 0. The derivative of this with respect to y will be 2xy. That's going to give you 3, and then the other two are going to give you 0. On Monday, we set these equal to 0. We solved for x and y to find the critical points. There ended up being 4 of them. I didn't solve for them completely, but there were 4. I'm not going to focus on that today. We'll come back to that next week. Instead, I want to focus on the geometric meaning of these things. What's the geometric meaning of them? They do give you slopes, just like ordinary derivatives in Calculus 1 give you slopes. But what slopes? That's the key question here. All right, we're going to look at the 3D plot to try to help us figure out what slopes. Copy and paste this here. I'm going to combine this 3D plot with a contour plot. 3D. What am I going to plot with contour plot? I'm going to plot some vertical planes for constant values of x and constant values of y. Let's do it for a constant value of y first. Say y equals -1. So I'm going to take the three-dimensional plot. Let's go ahead and see the three-dimensional plot here first. Take this three-dimensional plot, and then I'm also going to include a plot of a vertical plane at y equals 1, or -1. Remember, the positive x direction goes this way. The positive y direction goes this way. So y equals -1 is going to be a plane about like this. I'm going to plot that in the same picture with contour plot 3D. Though if we're going to see the entire plane, since my plot range here was 0 to 400, I better make z go from 0 to 400. You need 3 variables inside contour plot 3D because we are in three-dimensional space. There it is. You can also make that more opaque or less opaque with contour style instead of plot style. Opacity still works. Through it better. Okay? Those two surfaces intersect along a curve. And essentially, the partial derivative with respect to x is going to measure slopes along that curve. You can also get that curve to show up in here with parametric plot 3D. How can I parameterize the curve of an intersection here, which is kind of hard to see? About like this. How can I see it better using parametric plot 3D? It is going to be a parametric curve, and in fact, I can use x as the parameter, and that's the most natural thing to do. Because again, the x-axis is going left and right here, and this is a constant value of y. It's most natural to use x as the animation parameter. Y is going to stay constant at -1. X comma -1 comma f of x comma -1. Think about that. That's going to change the x coordinate as x changes, keep the y coordinate at -1, and make the z coordinate the output of the function at the point x -1. It's got to be the curve of intersection of these two things. X can vary between -5 and 5. Easier to see. Thickness 0.02, red. There it is. Looks like a cubic. Is it a cubic? Yeah, it is. It's a cubic function of x. What cubic function of x? Take the original function up there. When you set y equal to -1, what function of x do you get? Replace y with -1. Up there you're going to get x cubed. -1 squared is +1, so you get plus x. 3 times -1 is -3. You get -3 minus 10x plus 250, which simplifies to x cubed minus 9x plus 247. That red graph, thought of as a function of x, is the graph of that cubic. You can think about its slopes by looking at the partial derivative with respect to x. You take this partial derivative and set y equal to -1 in it, you're going to get 3x squared plus 1 minus 10, 3x squared minus 9. That's the partial derivative of z with respect to x, the rate of change or slope of z with respect to x, when y is fixed at -1. In other words, it can be interpreted as the slope of this curve at any value of x. You can plug in the value of x and get the right slope. Does that make sense? We can do that for different values of y.
Will the partial derivative of x be in the x plane?
Yeah, you could plot this. You could make a regular plot in an xz plane. That would make sense, yeah. And in fact, you could animate it as y changes. As y goes from -5 to 5, you're going to get different cubic functions. These all correspond to different intersections for different vertical planes. This graph up here. Let's add another vertical plane in here. Say at y equals 2. +2. So I'm just going to make this a +2. If we use parametric plot, I need to use a different color. I could put it in the same parametric plot, but I think just for clarity, I'll put them in different parametric plots. Replace the -1 with a 2. Make it blue, say, instead of red. Now we're looking at a second intersection there. They have a similar kind of shape. They're both cubics. They're not the same cubic. When you replace y with 2 instead of -1, all right, if I erase what's going on here, set y equal to 2 instead of -1, what happens? Look up there. Replace the y with 2 now. 2 squared is 4, so instead of an x, you get a 4x. Replace y with 2 there, you're going to get a +6. Still have minus 10x, still have plus 250. So now it simplifies to x cubed minus 6x plus 256. Is that right? It's a different cubic, slightly different. You can also do the same kind of thing in the derivative. Set y equal to 2. You're going to get 3x squared plus 4 minus 10, 3x squared minus 6, which you can get by differentiating this. And that's going to tell you the slopes of the blue curve in that x direction, if you thought of it as being in an xz plane if you wanted to. And of course, it should make sense that you can also cut this with planes that are constant values of x instead. For example, x equals 2. Change the y to an x here. Copy and paste the parametric plot as well. Let's see how we have to change that. I'm setting x equal to 2 and varying y So now y is going to be the parameter for the parametric plot. Like this, y goes from -5 to 5. Let's make it green. There we go. There's the intersection of the surface with a plane at a constant value of x. And you can see that looks like a parabola. Is it quadratic? Yes, it is. F of 2 comma y is a quadratic function of y. And likewise, you can make an animation of those intersections in a yz plane. Oops, I copied and pasted the wrong thing here. Change this to a y, change this to an x. These are thought of as functions of y. The slider is changing x. And they're all quadratics. The one where it's, well, no, I guess it's not exactly horizontal. If you plug in constant values of x into this equation, you get a quadratic function of y, because the y squared there, and there's no y cubed anymore. And the partial with respect to y is telling you slopes of that quadratic. So all this can be interpreted in terms of slopes, rates of change, as long as you imagine slicing the surface of 3 dimensions in these ways. Turns out we can slice them in a lot more ways, and we'll be doing that. But that's the end of the class today.